Okay, now we're going to ratchet up hypothesis testing a few notches. The book is actually, your textbook is very good and very methodical in presenting hypothesis testing. And you're sort of going to be getting it in different forms as it becomes more and more complex. Now we're at the level of considering hypothesis testing using samples, whereas before hypothesis testing was being presented by individual observations. Here you have hypothesis testing in the real world in the sense that you know population parameters. You don't know what a population's mean and standard deviation are. You're going to estimate that from samples. And so far the examples have included populations with known variances and means. Okay, well here's some 4 main points about this that you should sort of ponder as you go through this presentation and through the textbook reading. The first, you have to take samples from each of your hypothetical populations. So you'll have a hypothetical population for a control condition, and you have a hypothetical population for a change condition, for an effect condition. Like in a drug trial, a drug research study, you've got people who are not given the drug, that's a control condition, then people who are given the drug, and that's the effect condition or the experimental condition. We're going to sample from each of those. So you just have to keep that in mind. You're going to be comparing parameters that have been estimated from samples of each of those. Whereas so far you've been presented with a population distribution for the control condition essentially, and all the parameters were just given to you just so you could learn what hypothesis testing was about. Now you have to think about it actually doing it with statistics in the real world. We won't have that. You've got to estimate it. The second point is that you have to have as many observations in your sample as you possibly can. And we're going to do an exercise as part of this presentation where we're going to see how larger sample sizes give you better estimates of the parameters than smaller sample sizes. The third point is you don't know the population parameters. So you have to estimate these using samples, which of course is a point that I've already made. So you don't know these parameters, you're going to estimate them with samples. That was actually a major historical development in statistics when that was figured. Estimate population parameters from samples. It was actually figured out when a man named Gossett wanted to figure out how Guinness beer was being made, and he'd have batches of beer. He didn't know the population parameters of the batches, and so he needed to estimate them by taking samples of the beer, measuring things like alcohol level and sugar level and things like that. And of course what he wanted to show was that there was no differences between the batches. But he needed a test because he needed some kind of statistical examination, because obviously you can take samples of beer and they will be different, but you want to know if that difference could have occurred by chance, or is it something different they did in making the beer? You know, they made it have an alcohol level that was too high or too low. At any rate, he worked all this out. We owe a debt to him as somebody who figured this out for us for experiments that involve everything from making beer to psychology experiments. But it came down to estimating population parameters from samples. That was a major advance. Once you figured that out, then it was possible then to do statistical analyses and figure out probabilities without having to know what the population was really like. And finally, there's the units of the comparison distribution for this kind of hypothesis testing are more complex. The distributions you've seen so far have been individual observations. You've seen the distribution of the whole population. But now when you're going to samples, your comparison distributions now are going to be means of samples, and we'll get into that in a minute too. So it's more complicated than just looking at a distribution of individuals in a population and making inferences just from that. It's very rare and very unusual to know the population parameters. If you knew the population parameters, it obviously implies that you've done some kind of investigation where you figured out how every individual in a population has performed. And this is a very unusual thing to know. So usually we don't know what the population parameters are. We don't know what the population mean is, and we don't know what the population variance is. Well, here's a point about variance. First of all, you have to estimate it from your sample or samples. And the variance of a sample, so the standard deviation, for example, of a sample, tends to be a bit smaller than the variance of a population from which it came. So by we do sampling, we tend to pick samples that have smaller variability in them than the population does as a whole. And so one of the things that we have to do is correct for this bias in our estimate. And we do that mathematically, and I'll explain that in another slide. Okay, now I need to make a major point about the distribution we're going to use to calculate our probabilities. Okay, imagine you're actually going to do a study. You go out and you collect a sample, and you're going to estimate the population parameters from that sample. So you're going to estimate what the population mean and standard deviation is from the mean and standard deviation of the sample you've collected. Well, now you no longer have as a comparison distribution a distribution of individuals, because you're now taking samples. Okay, each of these samples will have a mean, and I need to know how likely that mean would have occurred by chance, and not an individual score occurring by chance, like we've studied before. So now that I have a mean of a sample, I need to know how likely a mean value or a mean difference from another mean might have occurred by chance. So I need a distribution not of individuals to calculate that probability, but a distribution of means of samples of a certain size, the size I've collected in my study. So each time you go out, imagine you were to go out and do this, you would collect, an infinite number of samples from a population, calculate the mean of the sample, and then plot that. And we're going to have an exercise later where we will go through and do that with a program that interactively lets you calculate means like that. And we're going to plot this distribution of sample means. And that distribution of sample means is going to tell me how likely it is that a certain sample from that population, a certain sample mean, occurred by chance. Just like the distribution we've seen before with individuals, now instead of individuals, it's going to be this distribution of means. Now this is a reference to how complex the comparison distribution becomes when you go to samples, which is a point that was made a couple of slides before. Now it's not a population or distribution of individuals, it's a distribution of means. Here are some additional points about the distribution of means. Now this distribution of means, again, is the comparison distribution from which we're going to get our probabilities. Okay, here's some main points about it. And when we go through this demonstration, on the next slide, we'll learn a lot more about this, but just keep these points in mind. The mean of the distribution of means is about the same as the mean of the population of individuals. Okay, so the mean is going to be set or be determined to be very close to the mean of the population of individuals. So the mean of the distribution of means is almost identical to the mean of the population we're going to make inferences about. Okay, point 2 is the variance of a distribution of means is always smaller than the variance in the population of individuals. So the distribution of means is always going to be narrower than the distribution of individuals of the population. It's always going to be systematically narrower. The variance is smaller. And we'll see that very clearly in the demonstration. Now the reason this occurs is because the probability of extreme scores appearing in a sample is lower than the probability of extreme scores appearing in the distribution of individual scores, because obviously they're in that distribution of population. For me to go out and sample, suppose I have a population of 10,000, school children, and I take a sample of 100 from that 10,000, well, it's very unlikely I'm going to pull out a very extreme score or a set of extreme scores. Probably I'm going to pull out a set of relatively, scores that are in the middle part of the range. So the variance of the distribution of means is smaller because it's very unlikely for me to grab extreme scores. Now, if you go out and do this sampling infinitely, and we create a theoretical model of this relationship, we can actually calculate a theoretical distribution, a theoretical variance that it ought to have. And the variance of a distribution of means is equal to the variance of the population divided by the number of individuals in each sample. The standard deviation of the distribution of the means is the square root of the variance. This is called the standard error of the means. Basically, the standard error of the means is a representation of how well your sampling is estimating the mean of the population. And we're going to discover that a small sample, or small samples taken from a large distribution, estimate the mean worse than large samples do. So the standard error of estimating the mean from a sample is greater when you have a smaller sample. Okay, which makes sense if you think about it. If I'm trying to represent a group of, say, 10,000 people, and I just randomly select 5 people from that distribution, it's very unlikely those 5 people are going to really represent 10,000 people very well. But if I go out there and take a sample of 500 people, I'll represent that sample much better. So my error will be less if I have a large sample than if I have a small one. The third point is that the shape of a distribution of means will tend toward normal regardless of the shape of the population distribution. So the distribution of means will tend to have a bilateral symmetrical distribution regardless of the shape of the population distribution. And that's because we're picking samples and representing a part of the population distribution. But remember the earlier point that the distribution of means is going to have variance that's less than, and it's unlikely for me to pick out extreme scores when sampling. And so what will happen is the shape of my distribution of means will tend to be normal looking. It will tend to be bilateral and symmetrical. And that's a point that's important for estimating probabilities. It means that regardless of what your population looks, when you sample from it, you're going to tend to take a sample that represents the mean well, and there won't be a lot of variability around that to screw things up. And so when you estimate probabilities, you can be pretty confident that the shape of the distribution of means will be normal. It enables you to use the equations for estimating probabilities from a normal distribution. Okay, now we're going to do an interactive program, a kind of demonstration that's going to let us change parameters and aspects of our sampling so that we can see what happens to the distribution of means. Okay, the first thing we've got to do is go to the website where this program resides. And what we're going to do basically is go to that website, download it to your computer, and then run it from your computer. So go to the web page that's indicated in this slide at learnpsychology.com. That's a website that has a lot of my other courses, including the stats course. And if you go to this page, you will see a listing of programs. And these are programs that I wrote to help people learn this stuff. And you'll see one there called Sampling Demonstration. And make sure you download the correct version you need for Windows or Macintosh computers. Download the program to your computer by clicking on that name. And then after it's downloaded, go to your desktop or wherever you've downloaded it. Click on the program icon. It should run. And you should see a display like you see here on the slide. Then on the next slide, we'll figure out how to use it to examine these aspects of the distribution of means. Okay, so you should have essentially 2 windows, one with this PowerPoint presentation up, or the presentation up, and the other window with the program in it. You can do this on Macintosh or Windows computers, but set it up this way so that you can follow along the PowerPoint presentation while you're doing the demonstration. Okay, here you see what you should do next. You should see a display like this. If you don't see a display like this and you didn't download the program correctly and it hasn't run for some reason, you got to figure that out first. It should download and run. There should be, I find that the most problem people have is they don't remember where they put it, but once they double click on the icon, it runs okay and they see this display. The first thing I want you to do is just click the instructions button there and read about the program. There will be some things that you don't understand in it perhaps, or some a little bit over technical language, but I think you'll get the gist of what you're supposed to be doing with it. Then on the next slide, we'll actually do a demonstration of its basic functions. Okay, now we have the exercise all typed out here. I'm not going to read everything that's on this slide. Basically, it describes what you can do with this demonstrator to show the effects that I've discussed in the previous slides. What you're going to be doing is basically just clicking on buttons on this demonstrator, and then it will do things. It will start sampling. What basically this program does is when you click on Create Samples, it creates the number of samples that you specified in the fields. Now it starts you off with just clicking on a button called Choose a Sample of 10, and it shows you what the simulation does when you click on that button. And so it shows you, however, what the basic operation here is. You choose a sample of 10 from the distribution up above that's blue. It turns them red. It then calculates the scores that would correspond to those subjects, those 10 subjects. Then it calculates the mean, and it plots that down below. And it keeps doing this for every sample of 10 that you choose. So if you keep clicking that button, choose a sample of 10, it'll keep choosing a sample of 10 and show you what happens to the distribution. That's really just to set you up. You could do that if you want to click on that 50 or 100 times. You'll see that it's created at the bottom just like the other buttons will do. But then the program is set up so that you can do a whole series of sampling and actually create a distribution down below, which is a distribution of means. The important thing to get from this is that the red distribution at the bottom that's going to be created is this comparison distribution of means. So it calculates the mean of your sample and plots it down below. Now what you're going to do, if you conduct this entire example, calculate a distribution down below based upon a small sample size of just 5 subjects, and then you're going to calculate one based on a sample size of 40. And what you should notice is that the distribution of means down below for a sample size of 5 is much wider than a distribution of means based upon a sample size of 40. That distribution with sample size 40 should be much narrower. Because see, what's happening is the larger sample the mean better, so it doesn't vary much. It pretty much calculates, since it's being sampled from the blue distribution at the top, it pretty much models whatever that mean is. But if you have sample sizes of 5, you're going to get all these disparate scores. It's much more unstable. And so the distribution of means down below will have a wider distribution. It itself will have more variance. It'll be more spread out. Anyway, do this a number of times. Practice with this and play with this program and see what happens to the distribution down below. This is a nice interactive demonstrator for this particular point, and what you should derive from this, of course, is that large samples represent the population better than small samples, and this is showing you systematically how that happens in a very sort of vivid animated form so that you can play with it, and it's interactive, so you can play with it to see what kind of effects are there. So I encourage you to click on Create Samples a number of times with different sample sizes and see what happens to the distribution down below. If you need to clear off the sampling, just click Reset, and it will clear it off, and then click whatever else you want. But just play with it and see what happens to the distribution of means down below. Well, after doing the demonstration, you should have a feel for how the population of individuals is modeled by a distribution of means sampled from that population. Now we're going to get back to the steps of hypothesis testing and incorporate that into our strategy. Now these are essentially the same steps as before, just that now we're going to focus on populations and samples instead of generalizing from individual distributions of individual subjects. Okay, with hypothesis testing, the first thing you want to do is restate your research question as a research hypothesis and a null hypothesis. Often when researchers formulate their questions of what they want to study, it's just in the form of a question. So the question might be, is my drug more effective in increasing the cognitive abilities of people that sustain brain injury, for example? And that's the research question, but you need to reformulate that into hypotheses you're going to test. And this is just done as a part of restating the question logically. So the first thing you want to do is restate the research question as a research hypothesis and a null hypothesis, and refer to populations. So that's the most important thing about this, I think, is that now you're going to refer to populations because you're going to be sampling later from populations. Okay, so population 1, for the example of brain trauma, population 1 are brain trauma patients who receive my new drug. Population 2 are brain trauma patients who receive a placebo. They don't get my new drug. They represent a control condition. So my hypothesis is that the mean IQ of population 1, those who get my drug, will be higher than the mean IQ of population 2, the control condition. And so when I express that in the symbols of populations, the population means mu1 will be greater than mu2. And mu is a Greek symbol used to represent the mean of populations. Regular old Roman characters are used for samples, and then Greek characters are used for populations. So mu here is representing the population means. So population mean 1, the brain trauma patients to receive my drug, will be greater than, their IQ will be greater than the population 2, mu 2. My null hypothesis is the mean IQ of population 1 will be the same as the mean IQ of population 2. So here the population means mu 1 will equal mu 2. So if I don't have an effect for my drug, the population means are the same. That's the null hypothesis. Okay, step 2 of hypothesis testing, same as it was before, but now it's going to be tailored to the situation where we're going to be sampling. Step 2 is determine the characteristics of the comparison distribution. This is the distribution of scores you expect if there's no experimental manipulation. So this is essentially the distribution of the control condition. Where there's no experimental manipulation, what do you expect the variability to be? Well, now we're sampling, we're not going to be using a distribution of scores of individual subjects. It won't be a z distribution like we had before of individual subjects. Now we're going to have a distribution of means. Now, remember that red distribution at the bottom of the demonstrator? When you're comparing samples of many subjects where you're going to be sampling, you're going to use the distribution of means as your comparison distribution. Because now you're going to be determining if your mean you calculate from your sample is significantly different from chance. So here we have an example down here. If I collect a sample of 60 trauma patients, my comparison distribution is a large number of means of samples of 60 patients from the population of trauma patients. Okay, so my comparison distribution is not going to be a distribution of trauma patients and their individual scores. It's going to be a distribution of means of samples of 60 from that distribution of individual trauma patients. Okay, so that's the big difference between the comparison distribution for hypothesis testing in the real world versus hypothesis testing, I guess, in the unreal world. The world in which you know the population parameters, you don't have to do sampling. That is kind of an unreal world. Here, because we're doing sampling, our comparison distribution now changes to reflect the fact that we're sampling and we're calculating a mean of a sample and using that to estimate the population parameter. So now we're going to have a slightly different distribution, the distribution of means, and we're going to use that one for step 2. So that's going to be the comparison distribution, and now we have to determine its characteristics. Okay, this is a continuation of step 2 in hypothesis testing, determining the characteristics of the comparison distribution. Okay, well the next thing you got to do is get a z-score. Remember, a z-score is a difference score. In this case, the z-score for the sample mean on the distribution of means is the sample mean minus the mean of the distribution of means. So you got the mean of the distribution of means. Well, that's just like a mean like you've done before. So you have your sample mean, and then you have your reference mean here on the distribution of means. You take that difference score between the sample mean score and the mean of the distribution of means, and you divide that by the standard deviation of the distribution of means. So it's the same thing that we've done before. It's just that now what you've got is a comparison distribution of means of samples instead of a comparison distribution of individual scores. So now you've got your sample, and you look it up here on this distribution of means distribution. Now you got to keep in mind also that through our exercise and everything, we discovered that the standard deviation of the distribution of means is much narrower. So the standard deviation of the distribution of means is the divisor here, and it's relatively small compared to the distribution of individuals. So here's an example here. You've got a mean for this small sample down here on the right of 18. The mean of this distribution of means is 10. And the standard deviation of the distribution of means is 4. So you take 10 from 18, divide that by 4, and that gives you a z-score of 2, which is 2 standard deviation units above the mean of the distribution of means. Now we'll go to the next slide and figure out what to do with this. Okay, step 3 of hypothesis testing. Now we have our z-score from the last slide, in which we compare the sample mean to the comparison distribution mean, and we got a z-score. Now we need to find out if that z-score would have likely occurred by chance or not. So we need to determine a cutoff for our sample score, or a critical value. How extreme must the score be before you conclude it could not occur by chance? How extreme must the score be to reject the null hypothesis? Okay, these are two of the same thing. Researchers usually reject the null hypothesis if the probability of the sample result is less than 5%. And this is referred to as the level of significance. So if it's unlikely this occurred by chance, by 5%, then researchers conclude that it did not occur by chance, it occurred by design, and so they reject the null hypothesis that the two means are the same. When they reject the null hypothesis, they support the research hypothesis. Now notice that it's 5%, it's not 0%, it's not 100% sure. Here we're only 95% sure that the result did not occur by chance. There's still that 5% hanging out there, which we'll discuss in a later part of the course. But the point is we make a probability judgment about the significance of the two mean differences, and if it's 5% or less, then we conclude this did not occur by chance, it occurred by some design in the environment, some design in the study, and it's meaningful. And that 5% is referred to as the level of significance. It's indicated there by a phrase, p less than 0.05. And you will see that over and over again. Now you can choose more stringent criteria like 1%. That's the other common one that's chosen. And so there's only a 1% chance of error. Here there's 5%. And we'll talk about what these significance levels mean in another section of the course. Step 4 continued. Determine your sample score on the comparison distribution. So we carry out the study, collect a sample, figure the z-score for the sample's raw score using the comparison distribution. So the sample has a mean of 18. Our distribution of means has a mean of 10. And we put our sample up next to that, and we get it's like a z-score here of 2. So the standard deviation of the distribution of means is 4, and we're 8 standard deviation units away from the mean of the distribution of means. So we figured our z-score is a 4. Now we're going to compare that to the z-distribution for the probability of that score of 4 given the distribution that we have here of means. Step 5 in hypothesis testing. This is the last step. So now we have to decide whether to reject the null hypothesis. We're going to figure out if our mean of our sample was so different from the distribution mean that we're going to conclude that it could not have occurred by chance, or it's very unlikely it occurred by chance, and we're going to reject the null hypothesis. So we need to figure that out. So what we're going to do is compare the z-score for our sample to the z-score that corresponds to a critical value representing 5%. So I have to go to a normal curve table to find this, and if you go to your textbook, you'll discover there's a normal curve table in the back, a table of z-scores. And from this table, I figure out that a z-score above 1.64 meets the cutoff for 5% probability. So z-scores of that level or higher only occurred 5% of the time. I can conclude that that's a very rare mean. Obviously a mean that only occurs, or a score that only occurs 5% of the time, has got to be a pretty unusual score. And so I can conclude that this score is very unusual and likely did not occur by chance. If the z-score meets this level, it's unlikely it occurred by chance. So I reject the null hypothesis, and I support or accept the research hypothesis. Now, since it's based on probabilities, rejecting the null hypothesis is not a proof. It's an inference. It's not a deduction. I base my decision on probability. And that's the essence of statistical kinds of judgments. They're really based on probability judgments, but they're very explicitly stated. So even though they're not proofs, that's very clearly known they're not, they provide evidence for an inference, and that's the best you can do. Okay, here's another example of hypothesis testing. Here we have a problem where we've got a study where we have college students who get statistics homework versus college students who get no statistics homework. Seems like that might be a relevant study for this class. So we have two populations, college students who get the statistics homework and college students who do not. Now I have a dependent measure, which is going to be my score on a statistics achievement test, like a score in a midterm or a final. Now I know from the previous applications of the test to the population mean and standard deviation on the test are 248. So it's been given to me that there are population parameters for this test. And these are 200 for the mean and 48 for the standard deviation. So step one is to figure out what are the null hypothesis and what is the research hypothesis, and express these in terms of populations. I've also got here that the research hypothesis is indicated as H1, and the null hypothesis is often indicated as H0. So just keep that in mind. Those are the same thing. So the null hypothesis, we'll start there. The null hypothesis is always a reflection that the means will be the same. So the null hypothesis in this situation is that the means of the two populations are equal. So students who get statistics homework don't do any better on the statistics achievement test than people who don't. And so the population means are the same. Now the research hypothesis will be that the means will be different. And so we're going to hypothesize that students who get statistics homework will have a higher score on average on the achievement test than students who do not get the statistics homework. So the two population means will not be the same. They'll be different. And those who get homework, they'll have a higher score than people who don't get homework. Step 2. Determine the comparison distribution. This is our sample of students who get homework and those that don't. Okay, we're going to establish a sample size here of 64. So we went out and did our study and we collected 64 cases. And now we have to determine the comparison distribution. And here we have a nice graphic depicting this. At the top you see the distribution of individuals. In the middle you see the distribution you're going to compare to, which is the distribution of sample means from the distribution at the top. Then finally at the bottom right you see our little sample of 64. Well, if you went out and did a model where you sampled infinitely from that sample at the top, calculated means of sample sizes of 64, and constructed the distribution at the bottom. If you remember how we did that with the demonstrator, there's a distribution at the top that was broad, and when you sampled from it, a relatively large sample like 64, produced a relatively narrow sample of sample means, or a distribution of sample means. Well, the distribution of sample means is going to pretty much match the mean of the distribution at the top, and so the distribution of means of samples of 64 will have a mean of 200. The variance, we're going to calculate that based upon a model as if we did this an infinite number of times. Well, the variance of the comparison distribution, the sample or the distribution of means, is going to be equal to the population variance. In this case, it's 48 squared. So we know the population variance was 48. Remember that from the previous slide. We square that number and divide that number by the number in the sample. In this case, 64. So we take 2,304, which is 48 squared, and divide that by 64, and we get 36. Then we take the square root of the variance. Remember, the square root of the variance is the standard deviation, which we have to finally get to here. The standard deviation of the comparison distribution of the distribution of means is the square root of 36, which equals 6. So our comparison distribution is going to have a mean, like the distribution of individuals, a mean of 200, and then it's going to have a standard deviation of 6. Now this is crucial for you to know. This is also crucial for the homework assignment. You're going to be calculating z-scores based upon estimating correctly the comparison distribution standard deviation and not the distribution of individuals. So here we have the three distributions. We have the distribution of the population at the top, population of individuals, the comparison distribution of the distribution of means from that population of 64, sample size 64 in the middle. And then finally we have our individual sample of 64, which is what we actually collected. Now we're going to move on to step 3, where we compare these to calculate our z-score. Step 3, determine the cutoff score for statistical significance. In this case, we're going to choose 5%. And like before, we discovered the z-score cutoff for 5% is 1.64. That's the critical value. We found that in the table of z-scores like the one you have in your textbook. Hypothesis testing step 4. Now we want to determine the sample score on the comparison distribution. We've discovered the z-score of 1.64 is the critical value. Now we want to figure out the score that we actually got for our sample. So our sample z-score is going to equal the sample mean minus the population mean. Here that's 220 minus 200 divided by the standard deviation of the distribution of means. That's the distribution, is our comparison distribution. And remember, we just determined that. So we take 20, which is the difference score between the sample mean and the population mean, divide that by 6, and get our z-score of 3.33. Now the next slide, we're going to compare this 3.33 to our critical value and make a decision. Step 5 in hypothesis testing. Now we have our z-score for our sample, and we want to figure out if the z-score is greater than our criterion cutoff score, our critical value. So we compare the sample z-score to the critical value and decide whether to reject the null hypothesis. Now see, this critical value was 1.64. Any z-scores at that level or higher are very unusual scores. They only occur 5% of the time. Now we've got a z-score here of 3.33. That's well above the 1.64 cutoff, and so it's very unlikely this mean difference, this mean score occurred by chance. It probably occurred by design. The probability is so low that it occurred by chance that we make a conclusion that it probably occurred by design, so we reject the null hypothesis so the two population means are the same. We support the research hypothesis that they're different. And that's the decision we made by probability. We conclude that there's really a difference here between the people who get homework versus those that don't get homework. And we conclude that if you give people homework, they do better on the statistics achievement test than people who don't get homework. And we base that on probability judgment using the process that's been described here. Okay, here's an issue that's relevant to hypothesis testing. It's referred to as confidence intervals. And it centers around the basic question you see here. How well can we estimate the population mean using the sample mean? That's obviously a very important question, because if you can't estimate the population mean using the sample mean, this is pretty much a dead enterprise. You have to be able to do that well. And determining how well samples estimate populations is a big issue in statistics. It's very important in understanding surveys and polls. Right now we're in an election year, and polls are used all the time to judge how the parties are going to spend their money when they back candidates and everything. And if you decide, well, we're not going to win this race here in Ohio, the party doesn't spend money there. Well, if you're not estimating the population mean of the voters' opinions of your candidates, then you make an error in judgment. Well, the best estimate of population mean is a sample mean. Now, samples vary in terms of how they're collected and how large they are. The specific estimate of a population parameter is called a point estimate. And we want to know how accurate are point estimates of the population mean when you use sample means to estimate it. And this falls under confidence we have in estimating the population mean from the sample mean. And so we specify a confidence interval, which I'll talk about on the next slide. Okay, here's a graphic that's illustrating a basic aspect of confidence interval. It's sort of the first step in trying to understand what these are. If you look at the sample mean below, it's very likely to represent the mean of a population that has the same mean that it has. And then the probability that it represents another population trails off from that in a normal curve. So a particular sample is likely to come from a population of samples that have the same mean. The sample below probably comes from the distribution C up above. Now remember, samples that represent the mean really well They vary in terms of representing the variability in distributions, but the mean they pretty much match. So it's likely that if you have a mean of a certain value, it'll match the mean of a population. And you can feel confident that the mean is represented. Okay, well, how accurate is a point estimate of the population mean based upon the mean of the sample? How accurate would that be? Now, I think you know intuitively that if you have a small sample, it's probably not going to represent the population mean very well. If you have a larger sample, it's going to represent it better, but then as you go up in sample size into really high numbers, you're not going to increase your accuracy of representing the population mean. So we've got to calibrate and figure if there's a formula that allows us to estimate how likely it is that our sample mean represents the population mean. Because if that doesn't represent the population mean, then we really have a problem in making all our judgments about whether population means are different and the same and so on. But also we have a measurement of how accurate our sampling is. Okay, well the error is calculated by a formula that we've used before. We take the standard deviation of the distribution of means, and that's going to be the amount of variability that our sample mean is going to estimate the population mean. And that's the standard deviation of the population of individuals divided by the square root of the number of individuals in each sample. Now you can see in this divisor, if I have a larger number of people in my sample, my standard error of the mean is going to be smaller. Better represent the population mean. So basically this boils down to the fact that a confidence interval where you feel confident you've estimated the population mean is going to be a factor of how dispersed the distribution of means is. It's not going to be dispersed very much if the sample sizes are large. If you remember the sample model that we used before, that the interactive model, when you had larger samples, the distribution of means was very narrow. And so with a large sample, you were estimating the population mean quite well. There wasn't a lot of deviation around that estimate. So no matter how many times you picked those large samples, it sort of didn't really make any difference. They were all coming up with the same mean that was representing the population. Well, the standard error of the mean is an expression of a standard reference for how dispersed that distribution is. And you can specify a range of possible means around your sample mean. This is referred to as an interval estimate, which is an expression of how confident you are. In the next slide, we'll calibrate that a little bit better. Okay, here we have an example. We want to specify a confidence interval for this estimating this population mean. Okay, so here we've got a sample mean of 220 and a standard error of the mean of 6. How likely is it that the true mean will be 226 or 214? How likely is it that the true mean, the one we're trying to estimate with our sample, is one of these others and not the sample mean? Well, we can calculate this. We know what the probabilities are for distributions of means of samples. We can actually express how confident we are in the mean we calculated for our sample is actually estimating the population mean. And we want to express this usually using a confidence interval that's relevant to our decision making about probability. And here we want to express it in terms of 95%. This is the conventional way of doing it. You can also express a confidence interval of 99%, corresponding to a 1% chance of being incorrect. Okay, let's express it this way. You can be 95% sure that the true mean of the population is between z-scores negative 1.96 and positive 1.96. Now remember, these are the critical values for 5% for our decision making about rejecting the null hypothesis. Well, when you look those up in the table for your particular situation here, with your particular sample size, which I think was 64. You have a sample size of 64. That corresponds, in this situation, when you've got a standard error of 6, it corresponds to a mean of 208 on one end of the distribution and a mean of 232 on the other end. So you can be 95% sure if the true mean of the population is between the values of 208 and 232. Now remember, your sample mean was 220. So if you take the standard error of the mean of 6, multiply that times 1.96, and then subtract that from the mean of your sample, and also add it to the mean of your sample, you express this in terms like the population mean is 220 plus or minus a standard of error of 6, and that corresponds to a mean of 208 on the bottom end and a mean of 232 on the top end. So you can say this is the 95% confidence interval for this mean. And what happens is people, when they do sampling and they go out there and calculate their sample means and calculate errors, they factor that into their judgments about how far off they might be in estimating the population parameters. And so, like in polling situations, you'll see that commonly expressed as this poll has an error of, such and such a percent. And that's a reflection of the confidence interval. And once the means begin to stabilize, and usually that happens when you get to a certain sample size. Maybe impressed, when the news commentators say they've picked a winner for a certain, vote in a certain race because there's, 10% of the vote is in. Well, 10% of the vote for a certain district might be quite a large number. And if it's more or less randomly selected from the district, it can represent the population mean quite well. And so even though it seems like a relatively small number, it's still large enough that you can estimate the population mean with certain confidence. And once they reach a certain confidence level, they then declare who the winner is. Now, there's always a chance that they're incorrect. And sometimes we've seen this before. In certain races that are close, they'll make mistakes because they don't incorporate the error that's in the judgment. Now, I assume they have pollers, who are monitoring this all the time, but there's always some error in it, some probability that you're incorrect. The true population parameter is still outside this interval. Now, it's still relatively small, but it's still there, and it still comes to bear when the situation is close. Now, in other parts of the course, we'll be talking about confidence intervals quite a bit. This is just sort of an introduction to them. I get a feel for what this is like, and I think you can see that, well, if I have a large sample, I'm going to represent the population mean pretty accurately. And the small samples, they're very unstable, and so it's likely that, I'm not estimating the population mean very well. Well, this is an expression of this in mathematical terms by specifying a probability interval for those kinds of estimates. And we'll touch on this at other parts of the course.